In this section, we're talking the comparison test. The goal is the same. The goal is to determine whether or not a series converges, but this time we're going to use the comparison test. There's something called the comparison test and the limit comparison test. Two different comparison tests you need to know about. The comparison test says that, okay, first of all, the assumption is that A sub n, B sub n, they're both bigger than or equal to 0. And A sub n is in between 0 and B sub n. A sub n is less than or equal to B sub n for all n. Then two things we can figure out from that condition. Number one, it turns out if the sum involving the B sub n, the sum involving the B sub n converges, then shouldn't the sum involving the A sub n converge? So if all of the B sub n are bigger than all of the corresponding A sub n, and the sum of the B sub n, B1 plus B2 plus B3 plus B4 plus dot, 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 all the way to infinity, if that converges, then the sum of the A sub n, A1 plus A2 plus A3, dot, 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 should converge as well. Does that seem reasonable? Yeah. That's what I'm appealing to. That's the hand-waving proof. You get a lot of formal proofs in Calc 1 here. You get a lot of hand-waving. And then you can go a different direction for divergence. If you think about the sum involving the A sub n, if that sum diverges, so if A1 plus A2 plus A3 plus dot, 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 if that diverges, in other words, if that goes to infinity, because we could assume it diverges to infinity since A sub n is non-negative, then shouldn't the sum of the correspondingly higher values diverge as well? That's what the second part says. If the sum from n equals 1 to infinity of A sub n diverges, then so does the sum from n equals 1 to infinity of B sub n. Once again, does it converge? In part A, we have the sum n equals 1 to infinity of 1 divided by 3n squared plus 2. Okay, if you think about what we call the convergence theorem for the integral from 1 to infinity of f of x dx, this is going to look the same. We first have to come up with inequalities involving not the series, just like it didn't involve the integral in the first step. Just the thing that comes after the series, the an and the bn, or I don't really specify which one's which. So I write down 1 over 3n squared plus 2, the thing that comes after the summation notation. And I'd like to compare that with a simpler nth term formula. One, ideally, in which I know what the series involving that nth term formula does, whether or not it converges. But I only have, a few tricks in my bag when dealing with a formula like this, as far as knowing whether or not a related formula is bigger or smaller. So one trick I have is deleting that plus 2. Which makes the denominator what? Smaller or bigger? Denominator. Denominator smaller. If you're making the denominator smaller, you're making the overall number bigger. Okay. So if I delete the 2, heck, let's delete the 3 as well. If you want, you could do it in steps. So this is going to be smaller than 1 over 3n squared, because I deleted the 2, made the denominator smaller, which makes the overall number bigger. If you want to, you could delete the 3 in the denominator. You made the denominator smaller once again, which makes their overall number bigger. And then if you think about the conditions for the comparison test, both of, or all of these formulas really have to be bigger than what? Or equal to 0. But in this case, they'll be strictly bigger than 0. Does everybody believe that? Okay. What do you want to compare the original nth term formula, 1 over 3n squared plus 2, to in this case? Yeah. Now careful here. Now I'm going to call this, just like I did for the comparison theorem, I don't like the way my less than looks right there. I'm going to call this step 1. Notice, step 1, there's no summation notation involved. There's no sigma involved. Students always make the mistake of trying to compare the series when you should be comparing the nth term formula of the series. Now, it's the second step where you look at the series involving the simpler function, the simpler nth term formula. Just like we did with the comparison theorem for integrals, improper integrals. So you want to talk about what the sum from n equals 1 to infinity of the simpler nth term formula does. In fact, we know what it does. What does that do? Converges, and then what's your explanation? Yeah, it's a p series, so just say p equals 2, and it converges because it's greater than 1, because p is greater than 1. Now, step 3, your conclusion. Something about the original series. So the sum n equals 1 to infinity of 1 over 3n squared plus 2 does what? Converges by the comparison test. The comp test, if you want to simplify it, I guess. I'm missing a by. Now, you should know what the conclusion is in step 1. If you're comparing the original nth term formula to something bigger than it, you want the sum of the something bigger to converge in order to be able to use the comparison test, okay? Otherwise, if the sum of whatever this guy turned out to be diverged, the comparison test tells you nothing, right? Because if you have this guy bigger than this guy, in order for convergence, the sum of this guy has to converge, right? In order for divergence, then whatever this guy turns out to be, the sum of this guy has to diverge. So if the sum of the bigger guy diverges, it tells you nothing about the sum of the smaller guy. Make sense? Okay? Any questions on that? Notice the steps. I really did design it to be the same as with the comparison theorem from 7-8. So if you understood that, you're going to understand this.